which I do, but I just try to introduce to all of you what is this integrability and other things. So let's see how things goes. And there is absolutely no rush. I can stop any time. So just feel free to ask questions. Let's just have a good time together, like whatever 45 minutes has. Okay, so let's start with basic classical mechanics. So what do you know? In classical mechanics, we know that we have, let's say, a Hamiltonian, okay, which can be a function of qi, ei, and t, right? And okay, for the time being, I'll talk about autonomous systems. So let's say it's just a function of qi and ti's. And given this Hamiltonian, we know that equation of motions are right? And also with that, given that it's it's a differential equation in fast order in time, we also need some initial conditions, right? And those are essentially, I will give you something like qi at t is equal to 0 and pi at t is equal to 0, and given that you can solve everything and you can get your solutions, right? As at a later time, or if you put any time as a matter of time. But there is a problem, which is this Hamiltonian in principle can be anything, but can I write down this solution in some exact analytical form for any given Hamiltonian or not? That's the question. Okay? Now it turns out that if you can write down the solution of these equations in nice analytical form, then those systems are known as integrable systems. Okay? So I will be more precise as I go along. But in order to introduce this concept of integrability, one thing is very important, which is the notion of constraints of motion. Okay, so I will just denote as COs, constants of motion. What is this guy? This guy is something, let's say I say that, okay, this F is some observable, not observable, something which is a function of q, p, t. These are some generalized coordinate and momentum. Then if I can always write down it as something like this, qi dot means dqi dt basically, and I also have dh I and pi dot, right? And now, can somebody help me out how to see that this guy is 0?
Equations of motion.
Precisely. So now I can just plug the equation of motion here. So I will get dh dpi, and this pi I can also erase. I can write it as del h del qi. And you see the minus sign plays an important role, because then I can just remove it, make it minus, this to cancel. Obviously I will have a del f del t as well. Okay. If there is no that explicit time here, then I can just erase this guy. I have this, and this is again, I can plug this equation of motions from qi and py from this, and I will get del f del qi del h del pi. Here I will have del f del I del h del pi. Okay? Can anybody?
Poisson Brackets.
Excellent, excellent. So this is nothing but f h Poisson bracket. Right? Beautiful. So that means, if I ask you, given a Hamiltonian setup, what are the constant of motion? If I give you a f, and if f is not a function of explicit time, the things you need to calculate is just the Poisson bracket, and if this guy is 0, then that's the constant of motion. Okay. So very good. So we are now in a situation where we can see that what is basically the constant of motion, and how that plays a very important role, because you see, in general, if you think about our phase space, okay, I mean it can be an n-dimensional phase space, because qis, pis can be, I mean 2 n-dimensional phase space rather. I can take any value, but if just we plot it in a kind of a 2-dimensional space, so here a point is basically this, and you put some constraint in this phase space depending on how many constant of motion you have. Now if Hamiltonian is only constant of motion, for an example, which is the case for, let's say, our favorite harmonic oscillator, right, p square plus q square, which is basically energy, then we know this is nothing but basically a circle. And because the phase space essentially will always travel here, because the constant of motion we have is just the energy. Okay? But you can have a situation where, except energy, apart from the energy, you can have all these other constant of motion. If, I mean, it can be, you can have many, and so that will basically constrain your phase space trajectories. Because it will just add up one constraint. So even if you, let's say I give you a situation where you have 2 n-dimensional phase space, okay, and you have only one constant of motion, then basically phase space trajectories are moving around on the 2n minus 1-dimensional hypersurface, right? In this case, it's just the circle, because the dimension is 2, and there is only one constant. So basically, it's just one. I mean this. But in general, if you have a 2 n-dimensional phase space, let's say, and let's say you have a small f number of constant of motions, then your phase space trajectory will be something like 2n minus f dimensions. Okay. Also, one thing is very important here. You can have at most 2n minus 1 number of constant of motion. You cannot get more functionally independent constant of motion, because then it makes no sense, because then basically it's just one point, everything is fixed. In order to get something out of it, in order to have some motion, you can maximum, you can have 2n minus 1 number of constant of motion. Nothing more than that. Functionally independent, that's also important. Because let's say I tell you that h is constant of motion, you can always tell me any function of h is also a constant of motion, because Poisson bracket will satisfy that. But they are not functionally independent constants. So functionally independent, you can have 2n minus 1 number of constant of motion at most. Okay? But of course, you can have a situation where you have only one. If it is a Hamiltonian system, then at least you will find one, given that Hamiltonian is not a function of time. But that's basically the idea. Okay? So now I think, given that we kind of understand what is constant of motion, so far so good, right? Everything is good. So then let's define integrability form. Okay? What is integrability? At least in this Hamiltonian context, Livoly's Arnold criteria. Arnold criteria for integrability. Which says that if there exist in functionally independent constant of motion, but this n is just nothing but the number of degrees of freedom, okay, in your system, so that all these constraint of motions are also, let's say, Poisson commute with each other, okay, what it says is that, let's say you have f1, 2, up to f small n, okay, this n number of constant of motion you have. And what are the constant of motion? The guys which Poisson commute with the Hamiltonian, that's the constant of motion. Not only that, it also need to Poisson commute among each other, which means this is also true. So they Poisson commute with each other, each guy commute with the Hamiltonian itself, Poisson commute with the Hamiltonian itself. So then you have small n number of, which the small n is nothing but the degrees of freedom. So you have all this constant of motion, they Poisson commute with each other. Then, if that is true, then you are guaranteed to have, so there exists a canonical transformation. So what is canonical transformation? We'll come to that. So there exists a canonical transformation. Okay. So that the equation of motions are completely integrable or completely solvable, whatever you say. So this is basically Ligonis-Arnold criteria for the integral. So it just tells you something very vaguely that if I give you a system and the degrees of freedom of that system is, let's say, n, small n, then if there exists small n number of constants of motion which are also Poisson commute among each other, then the problem is integrable. Okay? But it does not tell you many things. One, how to find this f, you don't know. It does not tell you that. Two, it does not tell you that how to get this canonical transformation also. It does not tell you anything, but it's just a statement which kind of, if I give you a system and if you can find that, then you know that things are integrable. Things are solvable, basically. That's it tells you. So it's known as Ligonis-Arnold criteria for the integral. Okay. So now, is this statement clear to all of you? Okay. Great.
Excuse me, sir.
Yeah, please.
If this canonical transformation exists, then it simply means that the coordinates basically for which we are solving the system, because equations of motion are constructed for coordinates.
Right.
Doesn't it mean that they are simply constants?
They are simply constants.
Because if you can map simply these, let's say, through canonical transformation to some other space,
Right.
this is actually the definition of canonical transformation. This is why we do canonical transformations, because we simply map it to spaces where the coordinates, some of the coordinates at least, not all, turn out to be simply constants. For example, if you have Q
You
and
mean the
T as-
cycling. You mean the
Exactly,
cycling.
exactly.
Absolutely. I'm exactly coming to that.
Okay.
So he pointed out a very good point that, okay, you can always have a canonical transformation which kind of, so let's say you started with a space of Qi Pi, some 2n dimensional space, and you can get to some situation where, so let's say some canonical transformation. Then you go to some space where you Qi Pi. The only thing is that they needs to obey the definition of canonical transformation, which kind of says that all these Poisson commutes and other things. But you can always do that. But what this integrability and all these things ensure is that you can solve the problem using something called action angle variable, and which is precisely, he pointed out, which is a canonical transformation. If you take the Hamiltonian, many of the coordinates become cyclic. Okay? So thanks for pointing it out. So the idea is the following. Okay? So let's say I have H, Qi, Pi. Then I do a transformation from this Qi, Pi to something called theta I II. Okay? So let's say there exists a transformation like this. So that now the Hamiltonian becomes just the function of II's. So all those theta's are no more there. So they all are cyclic. Okay? So if this Liouville's criteria holds, then you can always have this QI PY. You can make a canonical transformation and you move to this theta II space, and there the Hamiltonian becomes just the function of II's, which basically this guy. So there is no theta i's in the Hamiltonian. Okay. Now if this is the case, let's say this is the case, then it automatically implies II dot is basically minus del k del theta I, and theta I dot is del k del I. Right? And what will be here? It's zero. It's zero. That means II's are basically constant of motions, because that's the definition of constant of motion. Because this is nothing but di dt. Right? Not only that, we can do something even better. Given that this k, I mean, which is again Hamiltonian in this I theta space, it's just a partial derivative of del del I. So this will be also just a function of I. There is no theta, because k is a function of I. I mean, all the set of i's, and I'm taking a derivative of that, or partial derivative of that with respect to i's. So I get this. So that means theta I is nothing but omega I t, or something like theta I z, at least in this space. And now, given that you have a canonical transformation, you can always go back in your previous, I mean, you can do an inverse transformation also exists. So you can go back to your QI space and you can just write down everything, sir, just as simple as this. Of course, I don't know what are omega i's, that depends on the detail of k's and other things, but formally things are solved. Okay, let's take our favorite example, harmonic oscillator, right? P squared by 2 plus half omega squared x squared. So you see, I can always write down my P as, probably this is too low, or this is fine. This is better. It's fine. So it's 2 to over twice I omega cosine theta, and Q, let's say I write it as 2 over I omega sine theta. Plug this in here, you will get I omega. So you see, Hamiltonian initially was a function of P and, let's just put Q here, P and Q. If I do this transformation, now whether this transformation is canonical or not, that you need to check. And how you will check it? Because a canonical transformation means that it should be, and others are zero, basically. So that you need to check. But just take my word for the time being. This is a canonical transformation, and that just make the Hamiltonian of harmonic oscillator completely cyclic in theta. So there is no theta in the Hamiltonian. Okay? And that's kind of ensure the fact that you can solve it exactly. Not only that, I is a constant of motion, right? And what is I? I is just nothing but h by w. Yeah, we know that because energy is a constant of motion, and it just rescaling energy. It should be a constant of motion. And given that it's a one-dimensional, it has only 1 degrees of freedom. It's a 2-dimensional phase space. You can at most have one functionally independent constant of motion, and that is energy. You don't need to look for anything more, because otherwise it makes no sense. So things are good. So this is known as action angle variable formalism in classical mechanics. And yeah, so So you see that this is a way, essentially, you can solve the problem if the problem has constraint of motion, and you can already see that you have given this formalism, you have small n number of constant of motion, because all the i's are constant of motion, and you have small n number of them, and small n is also the degrees of freedom. So it's an integral. Everything is integral. Okay. So now so one Hamiltonian.
True only for the particle of unit mass you have chosen.
No. It's just you can choose m. Then presumably I need to check, but probably some m will sit here or something like that. No, it's not. But yeah, I mean, no, you can choose.
There it is p square by 2m. These need to be redefined.
Which one?
There it is p square by 2m if you are taking it for any general mass, and it will be m omega square k square.
Yeah.
There,
You
but you have
that
to,
energies are
Yeah.
restricted actually.
Yeah, I'm just taking m
yeah,
equal
but
to 1.
we have to choose then p and q accordingly, so that will.
Yeah, that's precisely what I'm trying to say. That then presumably you have to choose 2i omega by m, or also 2i omega m here, up, down. You need to check. But there is no reason to choose m is equal to 1. Just okay. So very good. What is the constant of motion?
Hamiltonian again.
Hamiltonian. Very good. Yes. So this is an example of integral. Okay. Now let's take an example, which is, let's say, something like h. So okay. So now let's take a two-dimensional example: q1, q2, p1, p2. And somehow, let's say I write down this Hamiltonian in this. Okay. So I can just separate out the q1, p1 degrees of freedom and q2, p2 degrees of freedom. And let's say it looks like this. Is it an integrable problem? So even though it's a four-dimensional phase space, but you can just separate out. Is it an integrable problem? Yes? And what are the constant of motion? That's one. You need to find one more. Because you need two, right? Because it's a degrees of freedom is 2.
Maybe angular moment.
No, actually, I mean, of course, if total energy is the constant of motion, then total energy minus h1 is also constant of motion. Or you can think of h1, h2 individually as two constant of motion. So yeah, this is an integrable problem, definitely. And this you can think of, it's like a two-dimensional harmonic oscillator. One can take this kind of example, like p1 squared plus q1 squared. And this is one guy. Also you have p2 squared plus q2 squared. Again, you will say that there is no m, but you can rescale.
But
No.
potential needs to be.
Of course.
Defined.
I'm being slow.
Potential needs to be defined. It will depend on potential.
Yeah. So this is, let's say you have this, and this also solves the problem. Okay. So now let's complicate the story a bit. Let's say again take a two-dimensional situation, harmonic oscillator, something, okay. So now, so let's say you have a stadium. Okay, and everything is free inside. So the Hamiltonian is p1 squared plus p2 squared. I can put 2m. Okay, inside this stadium. Okay, it cannot go outside. Is it an integrable problem? If so, then what are the constant of motion? If not, then it's fine.
Yes.
It is?
Yes.
And what are the constant of motion?
Again, individual kinetic energy.
Individual kinetic energy. So P1 square, P2 square is constant of motion. Is P1 is a constant of motion for this problem? No, right? Because you see, if I start here, I'll come back. So momentum is changing sign. So it does not remain constant. So momentum is not a constant of motion, but P1 square, P2 squares are. Very good. What about this? Circular. Circular stadium basically. And everything is free inside. So the Hamiltonian again P1 square plus twice 2m and P2 square plus twice 2m. Inside this circle. Is it an integrable problem? Anybody? If so, what are the constant of motion? Of course, Hamiltonian is a constant of motion. That's obvious. What is the second one? Think about some symmetry. This problem has circular symmetry. So, although it's a two-dimensional case, I don't want to use the word angular momentum, but kind of the z direction of the angular momentum should be, because it's a circular symmetry. So something like Q1 P2 minus P1 Q2. So it looks like a LZ component of the angular momentum. Good, we are doing very good. Now, let's take another example. Now let's just combine these two. Square, and put a circle inside. And the rest of the piece, Hamiltonian is again same. P1 square plus P2 square. Scale by 2 in order to get the energy. Is it a integrable problem? It turns out to be no. And of course, you will not able to find any constant of motion apart from the energy. And I can give you a very quick glimpse of it. Why? So the integrability also associated with some motion which is regular. In the sense, you remember when we solve the problem using action angle variable, the theta I we got is just omega t plus some constant. So things with time scales linearly. I mean, if you have to, then it will just, the things get worsen up in linearly in t. See it here. So let's say I start with here. I'll just bounce back. If I start slightly below, then see the trajectory will be now just completely gone. On the other hand, here also, if I start something here, so just an infinitesimal change of initial conditions, just making things completely different. I mean, the outcome is coming out to be completely different. So nothing regular here. Here you see that, so things should change something like linearly in time, but you can convince yourself with bit more mathematics that these are actually exponentially going, moving far away from each other in time. So there are the way you can characterize all this thing, calculating something only Punoma exponent and other things. But this is a classic example of quantum chaos where it's not an integrable system, and that's why you see all these things. Okay? So cannot find two constant of motion for this problem. And the same is true. Let's say you have a circle, and just if you just erase this part of it and make it a square or make it a straight line, and do the same here. So this is again some kind of a stadium, which is also known as in the literature something I don't remember now. But anyway, it's a very famous stadium. So in this case also, you will see the trajectories will just go far away from each other in time, and you will see a chaotic trajectory. Okay? But one thing is very important here. Even in a chaotic system, you might find some regular order. For an example, here, you can have this bouncing ball type of trajectory. We'll just do this. Very regular. But the statement is the following. There always exist finite measure or finite number of trajectories which will not be regular like this, will just go far away from each other as you change the initial condition, even a tiny bit. So this kind of things known in the literature as classical chaos. Okay, so very good. Just I will finish this topic of classical chaos and classical integrity, just introducing another interesting thing, which is our favorite Kepler problem, or the problem of central potential. Okay? So again, so I just want to emphasize that, of course, I mean, if this criteria satisfies, then the things will be integrable. But you can have even simplified story, because you see, let's say give you a central potential problem. Is it a integrable problem for any V?
Unless V is independent of time. Unless V is dependent on time.
No, V is just function of Q. I mean central potential, so it has to be function of the R.
No,
Is
yes.
it an integrable problem?
Not in
It's always independent.
no, not
So,
in
so how many degrees of freedom it has?
One.
No. Sorry, I think it was my mistake. It's a three-dimensional problem. So I just draw a vector, and you just think that this is. By the way, if it is a one-dimensional problem, then it has to be integrable, right? Because the energy is the constant of motion.
Until we find the potential is velocity dependent. And then energy
No.
dependent.
Of course, if it is a velocity dependent or time dependent, that's a separate discussion. But I put it Q. It's just the function of Q, right? So then it's a. But let's say it's just a central potential problem, okay? And it's a three-dimensional central potential. Then is it an integrable problem? One day I know it's integrable because energy is the constant of motion and energy is conserved. Everything is very good. But what happens in the 3D? You need to find three, huh? Because degrees of freedoms are three.
So there is a spherical symmetry in the potential, so it should be integrated.
Beautiful. And what are the constant of motion? H, L square, L. Perfect. Very good. But, so this is integrable. Now if I choose my potential to be, let's say 1 by Q, the hydrogen atom potential or Kepler potential. Then you have probably heard about another constant of motion which is known as Ranjan vector, right? So I have also another constant of motion, P cross L minus NKR, this kind. One can check that dA dt will be 0. So it's a constant of motion. And of course it also has this circular or it also has a central potential structure which kind of ensure that you have the L is also constant of motion, all the component of L. So if I try to count the constant of motion, so I have H, angular momentum is constant of motion, so L1, L2, L3, three component of angular momentum are conserved. I have A1, A2, A3. So total number is 7. But you see, we discussed that you cannot have constant of motion more than 2n minus 1, which is in this case 5, because n is basically 3. It's a three-dimensional problem. So it cannot be true. So that tells you that they cannot be functionally independent. And it turns out to be really that is the case. One can check that A dot L is 0. So that kind of get rid of one constant. So, okay. Another is A squared. This Ranjan square basically is some function of energy. I exactly don't remember the form, but it's also a function of energy. So these two conditions actually kill off two constants of motion. So even though you have 7, two are not, I mean, the functionally independent constant of motion will be 7 minus 2, 5. And it's a 2n dimensional phase space you have, because it's an n dimensional problem. I mean, n degrees of freedom you have, 2n dimensional phase space you have, so 6 dimensional phase space, and 2n minus 1, which is 5, and you have 5 functionally independent constant of motion. And that's the maximum you can have. That's why this problem is very special. It's known as super integrable problem and maximally super integrable problem. Because in order to get integrability, you need only 3. And which is indeed the case for any central potential. You have 3. So it's integrable. On top of that, it gives you 2 more. So the total number becomes 5. And that's why this is not only integrable, it's super integrable and maximally super integrable. So that's the maximum. And that's actually a beautiful structure you have in the context of this 1 by r potential, basically, and which also gets reflected in quantum mechanics in the hydrogen atom problem. Okay? So that's the only thing I wanted to add, and that's kind of wrapped up my my discussion on the classical integrability and so on. So if you have any questions, we can discuss.
Can you go back to that billiard?
Yeah, sure. Tell me, what is the question?
From that diagram, it seems like if the particle, if you wait for a long time, the particle returns back to its initial, path,
It will not.
then it's an integrable problem. It seems
Yes,
like.
yeah.
Because
Yeah, it's a some regular orbit. Yes, yes.
So there is a problem in quantum mechanics.
No, I'm not talking about the quantum integrability yet. I'm just talking about the classical. I will come to that if I get time. Okay. Okay, perfect. So maybe so it's now already 2:45. Maybe in 10 minutes I will try to talk about the similar things in the context of quantum mechanics, and then I will wrap. So one thing which is very important now, if I try to put all this story in the context of quantum mechanics, then the first problem is there is no notion of phase space because there is no notion of trajectory in the quantum mechanics, right? But one thing is very usually we naively do. Whenever we see something Poisson commute with each other, we just change it with the actual commutator. Okay? That's the usual extrapolation we all have. So now given that, if we kind of want to believe this notion of integrability, now what we will say that if there exists this F1, F2, Fn, again I don't know what is n because the degrees of freedom, the notion of degrees of freedom is also not very clear. But if there exist these quantities which kind of, so now if I go to the quantum setup, okay, so then I would say the constant of motion will be those guys, set of FIs, which basically just commute with it. Commute with them. Okay, that's the kind of common sense extrapolation. Of course, I am assuming that Qi does not depend on explicit time and other things. That's what I assume. So this is the definition of constant of motion, and the question is that if I can find this to be, because I don't know whether if I and j, well then also it's 0. So if Fi j they commute, so and also you have all those F which commute with the Hamiltonian, then we will say that this thing is quantum integral. Those systems. Now one more very interesting thing, as I pointed out, there is no notion of phase space. So in general, in classical integrality, we say that there is this nice regular orbits and so on. And when I'm giving you the billiard example, you found that when I have a square and a circle sitting inside, you don't have regular orbit and then things are chaotic. So in this case, the story is a bit difficult to visualize because you don't have this notion of phase space and trajectories, right? Because everything is probabilistic in some sense. But there is some analogy you can make just from this commutation business, is that whenever you find this kind of operator which commute with the Hamiltonian, it kind of increase the degeneracy of the problem. So all these conserved quantities comes in the cost of increasing the degeneracy in the system. And let's just think about our known example, the hydrogen atom example. What is the energy? Minus 1 by n squared, right? Okay, 13 plus. Just minus 1 by n squared. But we know in hydrogen atom problem you have n, l, m. These are the quantum numbers, right? You don't have magnetic field and other things, right? But all this L, M is not there in the energy expression. Okay? So the energy eigenvalues, if n is let's say 2, and if L is 1 or 0, it will be same. And the degeneracy for energy eigenvalues you can easily check, it's just twice n squared or n squared. If you have include spin, then it's squared. And this is basically coming from the integrability of that. So you have all those conserved quantities that get reflected, and it increases the degeneracy of the problem. So of course, I mean, you can calculate the degeneracy. It's just n squared. If you include spin, it's 2n squared. So you will get this degenerate state, which is basically the manifestation of the conserved quantities here, which again just h, l square, lz, and Runge. But of course, it's the quantum Runge, so it's slightly different. But again, it's some analog of the classical Runge. So that kind of tells you the way to characterize a quantum integrable problem. Just looking at the problem and try to see whether one can find out degeneracies and not. But you can ask the following question: you might have a degeneracy, but does it kind of guarantee the problem is integrable? So I just finish our discussion by giving you a general prescription, bit of numerical prescription. But if I give you some Hamiltonian, how to convince yourself that things are quantum integrable in contrast to quantum non-integrable or quantum chaotic problem. So what you should do, take the Hamiltonian. Okay. It will be some, let's say, n cross n matrix in general. Diagonal is the Hamiltonian. So diagonal is the matrix. Get the eigenvalues. So E1, epsilon 2, epsilon 3, let's say epsilon n. Okay. The same eigenvalues you have, given that it's n cross n matrix, and just arrange it in some ascending order. So this is, let's say, the smallest one. This is the next. This is the third. This is the fourth, and this is the highest one. So just arrange it in this way. Okay. Now calculate this quantity Si, which is nothing but epsilon I plus 1 minus epsilon. So basically the difference between two adjacent energy eigenvalues. So if we have a degeneracy in the spectrum, this should be 0. Right? And now plot the histogram of S. It calls level spacing statistics. Okay? So the prescription is clear. Diagonalize the Hamiltonian. Get the energy eigenvalue. Arrange it in the ascending order. Smallest one, let's say here, then calculate the difference. Plot the histogram. Just tell me something. If your spectrum has extremely high degeneracy, what you should expect at S is equal to 0 for this case?
Maximum.
Precisely, it should be maximum, because most of the guys are degenerate. Then there is a chunk of states which, it's chunk of S which are actually at 0. Right? Clear? Right? It is indeed the case. As it turns out, if the problem is integrable, this level spacing distributions will look something like that, which has a maximum here. On the other hand, usually, if the problem is not integrable, okay, quantum chaotic or non-integrable, whatever what you want to use, if you play the same game, you will see at S is equal to 0, it will be 0. So there is no degeneracy that in the spectrum. Even if it is there, if you increase n, that number is super small. So it is essentially measure zero in some way. So this is one way you can, if I give you a quantum mechanical Hamiltonian, you can just, plotting this, you can just convince yourself, kind of. Of course, everything has some here and these and that, but mostly, naively, you can kind of convince yourself one is quantum integral and another is not. Not only that, I just finish with saying, the drawing I just start from here, it has some peak and all these things. Even though you might find that this is something I just drew it, it has also some interesting meaning. If the system is non-integral, quantum non-integral, this plot you can get from something called random matrix theory. It turns out the level spacing distribution, even though if I give you some different microscopic Hamiltonian, it has some universal features and so on. And those can be understood in the name of random matrix theory, where you take a matrix, fill up all the entries from some Gaussian random number, and calculate the energy eigenvalues. Again, this way you arrange it, calculate the spacing distribution, and you will get the exact same level spacing statistic as usually you will get for any microscopic Hamiltonian. So in that sense, they are much more universal than what we think. But anyway, I think I should just stop here, and I will be happy to address any questions given that it's already